started. It's happening. Okay. I can give you back your exams, but I forgot to make the copies yet. Well, I mean, forget it. Just didn't have time to go through it.
So you want them back?
So I still need them back, so I gotta make copies. I didn't put the percentages on them. I figure you guys are big boys. You can calculate your own percentages. I don't know if Gail's going to be here or not. I'll just hang on to this. Well, I will get to give it back to her. There you go. Okay. And as I said earlier today, I think the average was 78%. I'm not certain. Okay, so if you have questions on those, by all means, let me know. We can go over them. Let's see, by and large, are there any particular issues? I think people generally struggled with the definition of Q, particularly as it relates to the composite beams. In this case, Q was, anyway, Q was for the bolted problem. What problem number is that? 2. Problem 2. I think people struggle with defining Q for problem 2. Because it's only the area, it's the total area and centroid of the attached member. Because the bolt has to support the shear load of the entire attached member.
It's the area of the attached. What does that mean for the picture? It's the area above the bolt.
No, it's the area of this entire beam, that whole area.
Plus this small area?
Nope, just this. Because the bolt is between this and this. It's shear flow. Remember I talked about shear flowing down and across and down? So that all of the shear in the all of the shear load in this member is borne by that bolt. Nothing up here is borne by the bolt.
Okay.
But all of this is borne by the bolt. So it's not determined. That's why the bolt position of the bolt doesn't matter. And that, in some sense, right? Because it still has to bear the entire shear load of that whole member.
So what about on the other side?
So there would be another shear load on the other side, but those are not coincident. So the shear stress at any point in the bolt is only the side contributed by one side, right? Because that's the shear stress here. There's another equal shear over on the other side of the bolt, but it's at a different location.
Okay.
So that the bolt doesn't have to bear the sum of the two. It only has to bear one or the other at any point.
Okay. So do the bolts, do they split the shear force in half and take half of the shear force on one side and half on the other side?
Well, it depends on how you do it. If you calculate the total area of both pieces, then yes. But if you just calculate the area, the Q for this one member, then you don't have to divide by 2, because that's the shear borne at that location. The shear borne at this location is the shear from that other member.
Okay.
Does that make sense? Okay. But I think the Q thing was probably the most confusing. Otherwise, everything else was, you know, I tried to indicate along the way what mistakes people made. But if you have any questions, come ask me. We can go over it. All right. Okay. So today and Wednesday, discussing beam design. And then Friday, Monday, and Monday, we are doing beam deflection. Maybe Friday, Monday, and Wednesday. I can't remember. So we have 3 or 4 lectures on beam deflection, and then that'll be basically it for this semester. Because we're not going to get into buckling, unfortunately. Okay. So beam design. Beams are the most important, most common load-bearing element in any kind of a Sorry, kick yourself later. Beams are the most common load-bearing element, right, in any of these things. We're talking about beams all the time, right there. You got beams and beams, you know, trusses and beams, right? So, designing beams is going to be a critical piece of engineering, you know, what you're required to do as an engineer. So there are 3 loads. Right, 3 internal loads that we typically concern ourselves with: shear, moments, and a normal load. And those are the 3 distinctive loads that we typically experience in a member. And you might actually break moments into torsional moments and bending moments, potentially, if you wanted to include them separately. But typically, in most applications, these 2 are going to be negligible. The normal load and the torsional load are typically not going to be all that great, particularly if everything's functioning as it's designed to function. And you almost often will face a torsional load when something breaks loose, right? You lose a bolt or something that allows a torsion on the beam. Beams are not designed with the expressed purpose of resisting torsion generally. Okay? So oftentimes these 2 are not going to exist. The normal load, whatever normal load is present in the beam, again, is not part of the design. That changes when we actually go to a vertical column. Okay, but when we talk about a horizontal beam, the beam is not typically designed to withstand normal load, so we typically don't have much normal load. And even when we do, it's unlikely that the normal load is as big as the normal stress induced by bending. So most of the time, we're going to ignore those 2 and focus on these 2 when we're designing beams, because we really have to be able to withstand these 2. Okay? Okay, so let's consider the typical beam. And we've got some load applied P. Right, this is our XY coordinate system. At the location where P is applied, there is a significant lateral load. Right, so maybe this P is another beam sitting on top of it or something. Right? But there's typically going to be a lateral load applied there that is not a shear, that's not it becomes a shear globally. But at this point right here, there's actually a compressive normal load or normal stress applied at that location.
In the Y direction, right?
In the Y direction, right? So there would be a resulting sigma Y at the location where that's applied. But that sigma Y dies off very quickly as we move away from that point where the load is applied. You understand what I'm saying? So sigma Y may be great here, but because this point is supported by a wide range of material around it, that sigma Y dissipates as it goes back into the beam. Okay? Furthermore, we will often, in reality, put a bearing plate at the point where the load is applied. The purpose of which is to specifically distribute that normal load, that lateral load. So that the lateral load, instead of being applied at a point, is actually applied over some distance, over some distributed distance.
What would the bearing plate be made out of? Is it
Well, steel. Now, if this is a steel beam, you have a steel bearing plate,
Yeah.
but it's thicker than the flange of the beam.
Oh, okay.
Right, so you got a flange. Typically, flange is fairly thin member.
Okay, so the bearing plate would be, an inch or two.
Be thicker. So the purpose of, well, I mean, it depends on the load
Yeah.
that's applied.
Yeah.
But the purpose of that bearing plate is to distribute that load over a wider range. Okay.
Because
So I'm sure this picture probably in the book of the bearing
the
plate.
plate's still going to experience the same amount of sigma Y, but the plate doesn't support anything. Is that kind of the basis behind that?
So the plate, yeah, the plate just transfers the sigma y. I'm looking for a bearing plate. I thought for sure there'd be a picture of a bearing plate. Yeah, I don't see one. Oh well. Sorry. Well, kind of, actually.
You Google one.
If you look on the picture on page 545, if you look at the picture on page 545, you can kind of see at the bottom of that beam, that's figure, it doesn't actually have a name, actually, number actually. Yeah, looking in quantum physics for a picture of the spectral materials. Anyway, the point is, it's not important. It's not really important. The point is just that the purpose of that is to distribute the load. So, sigma x, in this case, is still going to be much greater than sigma y at the point of application, so that we effectively only focus on the x component, the components along the beam. Okay, we're not worried about the sigma y that comes from that lateral load. Okay, so we also may have, there may be deflection constraints. We'll talk about beam deflection, as I said, beginning Friday. But there may be deflection constraints that limit your behavior more than the beam itself. So in other words, I might have a beam that's strong enough to withstand a certain amount of lateral load. Right? It's not going to yield, right? So I have an allowed stress in the material, and I'm not going to exceed my allowed stress for the beam. But it might be, and I'm going to exaggerate here, that that load would cause a deflection like this. And if that beam is, for instance, located over a window, I won't draw the window because I'm drawing on here. If that beam were located over a window or under a window, then my glass is not going to be able to accommodate that deflection, and I'm going to shatter my window. Right? So there may be deflection constraints that go beyond the beam design things we're going to talk about here. Okay, so the point is, the beam design that we're talking about here, in terms of yield or in terms of elastic failure of the beam, are not the only constraints, but they're the only ones we're going to deal with right now. So we are therefore going to focus on V and M, the shear and moment elements, in determining our beam design. In other words, we're going to make sure we're designing a beam that can support the V and M. And trusting, and once it does those two, in most cases we're going to trust that it's good enough to do these others. Right. You might come back at the end, kind of do an analysis, do your due diligence and confirm that it supports those, but we're designing the beam around these. Okay. So we want to keep tau and sigma from V and M respectively below the allowed limits. That's the objective. We're going to design our beam so that we're keeping tau and sigma below the allowed limits. So, how does tau behave? Well, tau, what's the expression we have for tau?
Tau is VQ over IT.
VQ over IT. Okay? For a given beam, if we wanted to know how is tau distributed across the cross section. So now I'm going to take this beam. Here, let me do a different one. I have some beam, very basic. Apply a P out here. Cross section in the center, and we'll look at the properties of the cross section. Okay. So here's our AA section. So So I'm going to zoom in on my AA section here, and I'm going to plot tau as a function of position along that beam. What is the shear stress at the top of the beam?
Wait, what is that picture?
This is the beam,
Oh,
right? This is the cross sections. This is the A cross section of the beam right there. What is tau at the edge, at the top surface? What is tau? What is the shear stress at the top surface? 0. Why?
because there is no area above.
Right, so Q equals 0.
Sorry.
Right? What about the bottom surface?
0.
0 also, right? Because there's no Q below, no area below. So we know tau is 0 at the top and bottom. What is the behavior of tau in between? What is the distribution of tau? So if you look at this, does I change as I move from top to bottom?
It'll be like a
Parabolic, right. So it's going to be parabolic. Because I and V are fixed. Only thing that changes as I move down, and in some sense, T is fixed. Right? Assuming it's a uniform beam, that's proportional to Q, which is equal to Y times the area, which is equal to Y times H times T, approximately. Right, if it's a square beam, if it were a square beam in cross section, just a rectangular cross sectional beam, then these would be exactly equal, right? Well, T is uniform across the whole thing, so it goes away. So effectively, T is correlated to Y times H, which is essentially kind of like equal to Y squared. That's where we get the parabolic behavior. Right, Y is the height to the centroid of the upper region. H is the height of that upper region. But they both effectively scale linearly with Y. Y is effective, if it's square, then Y is equal to H over 2. Okay, so you end up with a Y squared dependency. That's where you get the parabolic behavior. Does that make sense to everybody? Okay. Sigma. What's sigma equal to? What's sigma equal to?
P over A, or yeah,
No. Not B over A.
or P over A.
Not B over A.
Sigma.
My over I. Very good. It's like my over I. In fact, it is my over I. Right? My over I. You guys remember that? M times Y, not M sub
Sigma
Y.
doesn't equal P over A as well. That's different sigma.
That's the normal sigma would be
Yeah.
equal to N over A if we were doing normal stress.
Yeah, sorry.
Right. Okay. But do you remember this one?
Yeah.
Right. Okay. So there, M is applied. M is the same across the whole beam. I is the same across the whole beam. So sigma is proportional to Y. Right? So if I did the profile, the distribution of sigma, let's see here, in this case, I'm pushing down there, so my V is upward. Right, that's my V. And it's when I pull down here, so I have an M that looks like that. So I'm going to end up with a tensile load here, a compressive load there, right? And then all of my sigmas look like that. Sigma is a linear function of Y position, and 0 at the center, because Y is 0 at the center, because it's defined relative to the neutral axis. Does that make sense to everybody? Okay, so let's look at the top, at the center, and at the bottom. Let's take a little element of the beam. Right, so we're going to take this little element. We're going to take a little element here at the top, a little square element, a So square element at the center, square element at the bottom. And we're going to zoom in on that and look at the stress state on that element. So at the top, what is the stress state of the element at the very top? If I draw it, just draw the stresses acting on that thing. What's that? I mean, how would I draw it? Remember how we draw arrows and stuff on
There would
the
be
element?
no shear
Be no shear.
and only a sigma net x, right?
And a sigma in the horizontal direction, yeah, x. Right, so that would be this. Does that make sense? The element at the top looks like that. Element in the middle, in the center. What does it look like?
It would have no stress, no sigma, but max shear.
What direction would the shear be, positive or negative?
So it would be down, it would be like this. So this is
This is going to go up or down on this side?
down.
Okay, I'm being correct. Okay. So, how do you think about that? Think about that in terms of, again, remember this, sort of the can-ham picture? Right, we're pulling out this side more than we're pulling out this side. Right, because the bending moment is greater on that side. So there's a net force acting on this square on the top half that's greater in that direction. So I have to have a force that's acting backward in this direction. So this has to exert a force on the piece above it to the left, which means the first piece above it has to exert a force on this to the right, on the top. Or you can just take my word for it.
What?
Or you can just take my word for it.
Okay. So, okay. So can I, okay, is that the orientation for positive or negative shear?
So again, here we have a different, there's a difference between when we're doing internal shear. Remember, look at the moment, right? This is a positive moment, that's a negative moment, but in the terms of the internal moment, we consider it positive if it's cupping it concave up, and negative if it's cupping it concave down. So we didn't really, remember that
Yeah.
for doing the internal shear and the internal moment, we do it a little differently.
So is that just not how he oriented it, or do you have to orient it that way for it to come out correct? I guess my question.
That's the way that it all worked. That's the system that we work with. That's the
Okay.
convention that we're working with. So this would be considered a positive shear,
Okay.
right? In the absolute context of sigma x, sigma y, that's a positive tau x y,
Yeah.
right? But that particular element is being rotated counterclockwise. See what I'm saying? So there's two different kind of contexts. Depends on the context. But anyway, the point is, if you did the sort of force analysis, you'd see it would have to shear like that. Okay. And then what about the bottom? What would the bottom look like? What would the bottom look like? Clayton, I'm giving Clayton. There you go. Compression. It's in compression. Right? And as I gradually move from one to the other, if I looked at a section that was a little aggressive there, make it smaller. If I look at a section in between the top and the bottom, I'd have a slightly smaller tensile load and a slightly smaller shear. Right, somewhere in between those two. And then if I come over here, I get a same deal. Smaller compression, and now smaller shear. Like that. Does that make sense to everybody? So it's a gradual transition from top to bottom. What's the principal stress? If I were to now draw the principal stresses, for each of these conditions, let actually, let me erase that, let me not draw the orientations yet. Okay, what's the principal stress here gonna look like? Ben, what's the principal stress there? If I just do the principal stresses on this piece, what would it look like? Same as the top, right? Principal stress does look like this, because it's the only stress that's there. All right, now the center one, column. If I draw the principal stresses for that one, what would it look like?
No principal stresses.
No, there would be a version of this,
Well, I guess.
So if I have this
Okay.
stress state, now how would I have to, what do I have to do to draw it in its principal stress condition?
Would you draw a vector at the length of the magnitude of the shear stress?
The magnitude would be,
So say the shear was 850 megapascals, your principal stress would be 850. Right.
no,
Principal shear
it would
would be-
actually be, yes, it would be. It would be, but
So is there just one shear stress that's the principal shear?
how would it be oriented is what I'm saying. What direction is the principal stress going to act in?
It's just the same direction, right? As it already is in the center.
No, because in this orientation, there is no, right, what do I have? What's my normal stress in this condition right now as it's drawn on the board? What's my normal stress?
You don't have any normal stress.
Right, 0. Right. And my shear stress is something.
Right.
Or think of it in terms of a Moore circle. Where am I on the Moore circle?
Right.
Right.
Up and down.
Where do I go to get my principal stresses?
90 degrees. Oh, 90 degrees. You just orient it 90 degrees.
No, not 90.
45.
Right, right, because you're orienting
Oh.
Moore circle, you're rotating the Moore circle by 2 theta p.
Okay.
So theta p is 45 degrees. So here, that's my, and those are supposed to be the same, roughly the same length as the shear stress, like you said.
Okay.
Okay.
Why do you have 4 vectors instead of just 2?
Okay, so let's think of it in terms of the Moore circle. What's the Moore circle for this thing? You said it's the vertical line, so I'm sitting at this point and this point, right?
Yep.
And what is where are my axes? What is my sigma value at this point?
0.
So that means my axes are like that,
Right.
right? So when I rotate around 45 degrees, one is going to be at a negative value, one's at a positive value. One is compressive, one is tensile.
Okay. Yep.
Everybody see that? Everybody else see that? You go first. Okay. What about my principal stresses down here?
Same as it's drawn.
Same as it's drawn. Right? And then in between, what I would end up with if you did the analysis. So again, if you think of, in terms of the Moore circle on this one, the Moore circle for this condition, I am at, well, it'll look like this. My y stress is 0, right? There's no y stress here. But my shear stress has some value. So that's where I stand on this one. Everybody see that? So that means that if I were to draw this principal stress, it would be a small compressive stress, a large tensile stress, and a rotation of less than 45 degrees. A rotation of 2 theta p of less than 90. You see that? Okay. And these are supposed to be getting shorter as I move across here. I don't seem to be doing a very good job of scaling. And then here, in this case, I end up with it going almost all the way vertical with a small tensile stress and now a growing compressive stress. Can you see that progression across there? So as I move from the top to the bottom of the beam, as I move from the top to the bottom of the beam, I go from this to rotating around to this in terms of my principal stresses. Okay? So my principal stress is effectively rotated by 90 degrees and shift from tensile to compressive. Okay? That make sense? The tensile piece, as it rotates, goes away, and the compressive piece, as it rotates, comes in. You see that? All right. So that's what's happening across here. So the key is to identify what point I'm designing around. Right? I understand this distribution. If I'm going to design around the key normal stress, that's going to occur at the top surface in this configuration. If I'm designing around tau, it's going to happen in the middle surface, the center. Which we kind of already talked about. But for a non-rectangular cross-section, the distribution, this may not be a nice continuous spectrum. Right? It might not just be this nice gradual rotation. It depends on the nature of the beam. If it's an I-beam, for instance, it depends on the amount of load-bearing capacity in the flanges. Yeah.
Could be discontinuous?
Can it be discontinuous?
You just made it sound like it might be. I can't.
Well, it's just hard because in an I-beam, can it be discontinuous? Because you change orientations when you go from the flange to the web. Right. So the shear flow does this. The shear flow takes a right angle turn.
Right, I remember seeing that in the book.
So
it is discontinuous.
It's not really discontinuous.
Not really.
But the orientation changes as your perspective changes as you go from, in other words, here this is sigma xy, here it's sigma xz or whatever.
Because isn't it come
Or, I'm sorry, tau xy versus tau
doesn't it
xz.
come down like this and then come back up on for an I-beam? Like you'd have that for tau. You're applying tau across the I-beam. For the middle section, it looks just like that. For the
But it doesn't go to zero at the edges.
doesn't?
No. The web doesn't go to zero. At the top and bottom of the web, the shear stress is not zero.
Oh, yeah, I guess. And then, but then there's like a corner
So the
there.
distribution, if I had an I-beam, if I plotted the distribution on an I-beam, it would start here at zero, come up, right, and then I have something that does something like this in the center. Okay, you see what I'm saying?
Mm-hmm.
As I go through the center of the I-beam. So it's a little weird with the I-beam. Okay, anyway. So there you have that. Okay, so we know we're gonna have to look for, we have to understand the distribution of stresses. This is more conceptual stuff than it is quantitative. Right? We just want to understand conceptually what's happening as we go through the member. The principal stresses are changing their orientation and shifting from compressive to tensile to compressive. And now, when we actually go to pick our beam, design our beam, we're going to use that information we will first, in most cases, design to meet the bending moment. Most beams are fairly long. That's the purpose of the beam, to have a long breadth of distance that's covered, that's supported. And so since you've got such great distance, the moments tend to get fairly large. Right? So in most cases, for long beams especially, we want to design first to meet M, and then we'll come back and check and see if it can support B. the design that works to support M. So we have sigma equals M y over I. Or where's this going to be? Where are we going to care about this? Where's the maximum value of this going to be? Right. So remember the book said MC over I. C is the maximum extent of the y direction. Okay. These are the geometrical constraints of the beam. And C and I are the properties of the beam. M is the applied load. So we're going to define a section modulus S that is I over C. So that the required section modulus is going to be the ratio of the applied moment to the allowed stress. So for every beam geometry, we can define a section modulus. Give me an I-beam, give me a C channel, give me just an L bracket, give me a T-beam, can't do T with my hand. Give me any particular cross-section, I can define a section modulus for that cross-section of beam. Right? So that every beam is going to have an S. Therefore, if I know what moment is applied and what material I'm using, the sigma allowed is going to be defined by the material. If it's steel, it's going to be bigger than if it's aluminum. Right? If I know my applied moment based on my building design or whatever, and I know what material I'm using, then I can say, okay, well then I've defined the required modulus of my beam. I need to go find a beam that has this required modulus. Okay? And so this is what's going to be tabulated for beam designs, particular beam geometries. So we want to find an S that's greater than or equal to the required S to make sure that it's going to be able to withstand the moment that we're going to apply to it. Okay? And then once we've done that, right, so we've designed first to meet the moment, then the third step is to evaluate tau is equal to QV over IT and make sure that that's less than or equal to the allowed shear stress. So everybody understand that process then? So we start with the moment, figure out what required modules we're going to have. Then we can typically tabulate, we can calculate the required modules, but the point is, you don't know whether you're going to use, unless you know a priori, I have to use an I-beam in this application.
You're like limited to a supplies.
Yeah, or if you're limited to, in terms of the design, it's the only thing that will fit. Right? Unless you're limited, then you just need to find something that has a modulus that's at least, a section modulus that's at least as big as the applied moment divided by the allowed stress. And again, sigma allowed is determined by material, so you can actually tweak that as well. Okay? So, most of the beams we're going to choose are going to be standard drawn beams. Wrought beams, wrought iron. So the way that these beams are made, we'll call these stock beams.
So they're not cast?
Nope. Stock beams, you take a hot iron ingot and run it through a bunch of dies. So you start off with this, and then you kind of, I mean, I'm exaggerating the process a little bit, then you kind of walk down to this, and then you kind of do this, right? And again, this is not really what happens. Okay, but you can kind of imagine.
Yeah, they just shove it through a bunch of Play-Doh makers that are almost the same size.
Fuzzy bumper barber shop. Okay. And then eventually.
Hey, they actually, I just saw a commercial on TV for one that was with Play-Doh and they made beams.
No.
Yeah?
Yeah.
Where I worked, they had a machine that would do that with copper. They'd make it so hot that it would just go through the die and come out like Play-Doh, like the barbershop.
And really, I'm exaggerating. Like I said, it doesn't go through nice smooth shapes like this. They'll roll it flat on one side and they'll roll it flat on the other. And they anneal it in between to soften it back up again. We'll talk about a lot of that material science. Anyway, the point is you end up then with a single monolithic cross section that is some length, depending on how much ingot you put in the first place.
Can I sit in on the last 7 minutes?
Sure. So,
It's yourself. I never realized it was this far back. Is it always that far back?
Yeah.
Really?
Yeah.
It seems like
This is like,
All right,
Because I can't-
shut up. Shut up.
this is Inception.
So this is, we're not even going to get to a problem, for crying out loud. Anyway, so this is what you end up with, a monolithic beam, okay? It's okay, because we can do all problems next time, so Wednesday will be all problems. It's a monolithic beam, and so they have a certain number of shapes. And these are considered wide flange shape, these are wide flange beams, okay? Or you might get a C channel, or you might get an L bracket, right? Or as I said, a T. There's different kinds of shapes. But the I-beam is probably the most common. Okay. However, those are typically made in certain stock geometries. There may be an application where I need a long, really tall beam, or a narrow flange beam, or something that doesn't come in stock geometry. So then the other option is to use a composite beam structure. Or I just take a bunch of plates and weld them together. So I can take a narrow plate and weld it to a big, long, tall plate. Yeah, you sure?
What?
Exactly. All right. So you get, you weld it in here. You weld it at each of the joints. Right? Or you could, make something that's bolted on. You could use a short L bracket on each side, bolt through there to a central beam, do the same thing at the bottom. Right? There's different ways of doing it. If it's wood, right? How to make a beam out of wood? Nail it together, right? Exactly. Take a 2x4, nail it to a 2x12, nail it to a 2x4, right? Just nail it together, right? Or you can do the laminate beams. You can glue them together, right? You want a really big, strong beam, just glue a whole bunch of 2x4s together, or 2x6s, or whatever,
Or we could take a huge tree and
cut it.
Right, exactly.
cut it down.
Not exactly a green solution. Anyway, so I can laminate beams. So I can glue, I can weld, I can bolt, I can nail, all kinds of different ways for the composite beam. So in this case, I'm not going to be able to look up some tabulated value of S. Right? I'm not going to be able to look up some a predetermined section modulus. So in these cases, I'd have to calculate the section modulus by calculating I and C. Okay. All right, and when you do look them up, in this case, so for instance, the I-beam might be labeled as something like W12-22. So if this was in English units, a W12-22 is W means wide flange. 12 is the 12 inches, the height of the beam. And 22 is the number of pounds per foot of the beam. So when you look them up, that the name means something. And if we were doing the C's, it would lead with a C, and if we were doing the L's, it would lead with an L.
So that you can get your C and M from that.
Your C and M. I'm not sure what you mean by your M. You know, you can get your I, or your C, yeah, this C, right? But most of the time, since they're stock beams, you just look at the section modules. Right? They'd already have it calculated. I mean, they'll tell you, if you look in the spec, if you look in the back of your book in Appendix B, you'll see on page 804, and nobody has the book. So if you look on page 804, they actually give you the dimensions of everything. The thickness of the flange, the thickness of the web, the height of the whole thing, the width of the whole thing, the moment of inertia, the section modulus, radius of gyration, which we won't get to because we're not going to do buckling. We're going to run out of time before we get to buckling, but the radius of gyration is used in buckling. Buckling analysis. Okay? Does that make sense? Any questions?
Yeah. So what is all this?
Yeah. Catch the video, you'll see. Okay?
Tune in next week. Round 2.
So we will do the problems then on Friday. Okay?
Not Wednesday?
On Wednesday, sorry, on Wednesday.
It's good Friday.
I'll be here Friday.
Friday is, we'll start deflection. We'll start beam deflection on Friday. Okay? All right.
Back to test.
What's that? I did indeed. You can have, I gotta have the test back. So please turn in the tests.
Oh, you're collecting, sorry.
What are we doing?